Funding for this program is provided by Annenberg CPB to advance excellent teaching.
How do we know that these are all the same things, even though they look quite different? Why have people always been able to link different elements and ideas into a coherent relationship? A process that we only now have begun to understand.
Try a price change and see what happens.
Cognitive processes, this time on Discovering Psychology. In the 17th century, the great philosopher Descartes declared, "I think, therefore I am." Without an awareness of our own thought processes, he reasoned, we would have no sense of personal identity. It is our thoughts that give meaning to everything, memories, experiences, expectations. Among all other creatures, only we humans have the ability to think as widely and deeply. And so we salute ourselves as the true thinking animal. I think, therefore I am. Or in Latin, cogito ergo sum. Cogito means I think, and its derivation, cognition, is a general term we use for all forms of knowing. That includes remembering, deciding, planning, problem solving, and communicating ideas. The study of all these higher mental processes is known as cognitive psychology. Cognitive psychologists study how people take in information, store it, transform it, and manipulate it. Even though people have thought about thinking for countless centuries, it's only recently that researchers have begun to discover how we think. Howard Gardner of Harvard is one of the country's leading cognitive psychologists.
The word cognitive psychology goes back quite a long time, and it basically refers to any kind of research or thinking which has to do with how people solve problems. And you have cognitive psychologists under that name or another name going right back to the beginning of the century. After the Second World War, when the computer had been invented, a number of people from different disciplines began to say, well, now that we know that computers can solve problems and we understand something about how they work, maybe we should think about the human mind as being a certain kind of computer, a certain kind of information processing system. And these individuals who came from psychology, philosophy, artificial intelligence, linguistics, sometimes from other disciplines as well, styled themselves as cognitive scientists. In the 30s and 40s, behaviorism was the most important area of psychology, and psychologists actually believed it was only important to pay attention to actions and behaviors which you could measure. And they made no distinction between animal behaviors, infant behaviors, and those behaviors of mature adults. Moreover, the behaviorists were very afraid of talking about any kind of internal representation. They didn't want to talk about ideas or models in the mind or anything inside the black box. Cognitive scientists said that's a dead end. People think, they compute, they solve problems, they have images in their head, they have schematas, they operate upon these things. That's what thinking is all about. And for goodness sake, if you allow a machine the right to think, you've got to allow human beings the same kind of right. So I think a very important part of cognitive science was just to point in a positive direction rather than in a dead-end direction.
In 1958, British psychologist Donald Broadbent used the information processing approach to model human thought processes. He was the first psychologist to use a flowchart to describe what happens to information as it's first received by the senses, then selected as competing information is filtered out, and stored in our memory. This information processing approach has proven so valuable because it analyzes cognitive processes as a sequence of ordered stages. These stages can be traced as information flows through the mental system as if the mind were a computer. Nobel Prize winner Herbert Simon of Carnegie Mellon University has been working since 1955 to make a thinking machine that can solve problems the way humans do.
We began to get interested in the possibilities of using the computer as a way of modeling and thinking about human thinking. And the reason we thought the computer might be useful there is that we began to realize that computers can deal with a good many things besides numbers. They can deal with any kind of symbols, whether they be numbers or letters or words or pictures. We thought that we could formulate what was going on in the thinking process more effectively with a computer, symbolically, than we could if we tried to build a mathematical model of it. Most biologists today think that organisms are machinery of a very fancy kind, but they operate according to natural law, according to natural processes. The mind is part of that machinery, and it gets its work done by doing simple things like inputting information, reading, writing, comparing symbols, storing symbols in memories. And we know that computers can do exactly those kinds of things, using entirely different hardware, of course, using glass and metal instead of living tissue. But the underlying processes are the same, and it's those processes which we model when we simulate thinking. We used to, in computers, use these punch cards a great deal. Well, you could ask, how could a punch card carry information? It's made of paper. Well, the information was in the pattern of things in the card, in that case in the pattern of holes. Now you can make patterns out of a lot of things, not just out of one material. So in computers we use electromagnetic patterns, we use patterns in metal. In the human brain we use patterns in neurons, but we can simulate the same kinds of patterns in both cases.
Using the information processing approach as a springboard, cognitive psychologists have begun to answer fundamental questions, such as how our experiences get turned into knowledge that can be called upon later to guide our actions. One of the central operating principles of the mind that cognitive psychologists have studied is our ability to formulate mental representations of the external world, the physical and social reality we experience. These mental structures are so much a part of us we're not even aware of them. But cognitive researchers distinguish between different aspects of these representations. Take a look at these versions of the letter A. How do we know that they're all A's? They're not identical. In fact, some of them are quite different from each other. Yet somehow we can identify them instantly. A typical computer, however, wouldn't be able to recognize them as belonging to the same category. Here's a harder example of the same mental process. Try to think what distinguishes the top line from the bottom. The correct answer is that the top line has rounded letters, while the bottom one has letters with straight lines. And here's another example. Which phrase doesn't fit with the rest? The answer is stars twinkle, because the others happen during the day. In all of these examples, your mind has had to perform one of its most basic functions, categorizing. We have to know what things are similar and what things are different if we're going to avoid the next danger and pursue our next pleasure, not to mention pass our next test. The categories we form in our mind are called concepts, mental representations of related things. A concept may represent all examples of a physical object, say a shoe, or an event, such as walking, a living organism, such as a person, an attribute, such as fast, or even an abstraction, such as love. Some concepts are remarkably complex, as demonstrated by these symbolic cave paintings made by Australian Aborigines. These, for instance, are gods who make lightning, which in turn brings rain, which in turn makes life possible. Our imaginations can construct concepts that link virtually any elements into a coherent relationship. The Aborigines also have a category that includes women, fire, and all dangerous things. In their mythology, the sun is the wife of the moon, which links women as wives to the sun. And of course, the sun gives off heat like fire does. So fire is linked to women too. And because fire is dangerous, all dangerous things are thrown into the pot for good measure. But how do we store a concept in our minds? Do we have a definition of a bird, for instance, locked in our brains that can be read whenever we need it? Actually, it's now believed that many of our concepts include a representation of the most typical member of a category, called a prototype. For example, we tend to have in our minds a prototype of bird that most resembles a robin, while few of us think of a turkey as the prototypical bird, except around Thanksgiving, of course. We also tend to organize concepts in hierarchies. Is this a piece of furniture, a desk chair, or just a chair? For most purposes, we think of it as the latter, just a chair. This so-called basic level in the hierarchy of the concept chair gives us as much detail as we usually need. It's generally believed that most of our thinking about concepts is done on this basic level. Concepts are one way our minds categorize things. But what happens when the information we process contains many concepts? How do we handle complex ideas and experiences? The answer is with schemas. Take this sentence as an example. Jim was upset when he realized he had forgotten to pack the mustard in the basket. Why do we instantly understand what it means? We understand because we've organized a body of information and expectations around a picnic basket schema. Thus, we can infer a great deal about the basket without any other information. We can infer what's likely to be in the basket
Yummy sandwiches.
and what's not.
Bicycle wheel and a snake.
Moreover, when new information clashes with an established schema, there's a violation of our expectations, and our mind reacts instantly.
I love the taste of wicker.
Just compare your reaction to this sentence to this one. This violation of your expectations is detected instantly by your brain even before you're consciously aware of it. Now, sometimes we don't have enough information to activate the right schema until we add the right cue. And sometimes we activate the wrong schema entirely. Take a good look at this drawing. It's an example of how our interpretation of new information can become faulty or biased. Try to remember the image you just saw. What do you think was happening there? For a number of research subjects, the knife was perceived to be in the hands of the black man. These subjects reconstructed the information found in the picture